Welcome back to Nexperia Power Live, and you're watching our industrial channel. We're about to start our third session of the day.
Here, live with you, are Steven and Stijn, who will discuss the importance of high current ratings, give an insight on how the rating of max continuous current is carried out, and what to look out for in such MOSFETs. The session will take about 25 minutes. They will start with a presentation, and we'll take your questions afterwards. Questions are anonymous, and you can ask yours using the question pane on the right-hand side of your screen. So please go ahead and ask your questions to our experts or share your own experience and insights. And with that, I will hand over now to Steven and Stijn to begin. Gentlemen, please take it away.
Hi, welcome to this session on high current MOSFETs. I'm Stephen Waterhouse. I'm the International Product Marketing Manager at our PowerMOS business. And I'm joined with Stijn Nesbach, who's our application engineer working at our PowerMOS business too. Okay, so there's many applications that require high current MOSFETs, and these don't always require that to be high current constantly. So we talk about very high current in terms of 300, 400, 500 amps. We wouldn't expect the MOSFET to be using that current 100% of the time. However, there's certain situations, for example, with battery isolation or with motor drive, where there's fault conditions. So with a battery isolation, if there was a short circuit, then there'd be an overcurrent situation. And with the latest battery technology, lithium-ion batteries, it'll give you a very high instantaneous current. And it may take a few seconds for us to isolate that battery from the load. And also with motor drive applications, there's situations, especially with power tools or with mobility products where there's a locked rotor, and the MOSFETs may need to handle 700 amps for just a few seconds. So we're talking about these fault conditions rather than continuous 100% of the operation time. Next slide, please. So some of the applications I already mentioned, and we start to see that the MOSFET voltages are in the sort of 40 to 100 volt range for e-bikes and floor cleaners and golf buggies and power tools and lights. And the power could go up to 10 kilowatts. So these applications are becoming more and more demanding in terms of the voltages and currents that we put through the MOSFETs. Now, in order to keep losses as low as possible for the MOSFET, you would tend to go for this lower voltage MOSFET to keep the RDS on low, which means that you end up with a lot higher current. There's an increased impact of application fails. So if this was an electric wheelchair, we don't want the application to fail and leave someone stranded, or even worse, any sort of fire to happen or something like that. Which means there's product reliability, there's a legal reliability. We worry about safety, and also not just ours, but our customers' brand reputation. Next slide, please.
Stephen. So as we've seen now, currents are increasing. So then we can start looking at, okay, what does this mean for the MOSFET current rating? And the MOSFET current rating on the datasheet is called ID. And the definition of the ID rating is the maximum continuous drain source current the MOSFET can sustain while fully enhanced at a mounting base of 25 degrees and die at max junction temperature. Now, this is quite a mouthful, but what this means is we have a LFP profile where we have a tab, silicon in between, and then we have the copper clip on top. And this is a standard LFP structure. And what this means is that we want the maximum amount of current flowing through here, through the tab, through the silicon, and through the top clip, while the mounting base is at 25 degrees, and the silicon is still under its maximum junction temperature, i.e. under its usually 175 degrees Celsius. Now, this is a single parameter which captures thermal performance because you have a lot of power dissipation and the heat has to go somewhere. You also have the temperature rating, because if the silicon die is rated to a very low temperature, you don't have that much room to play with. And it also captures the RDS(on). So you have the silicon resistance, which is the resistance of the silicon itself, and the package resistance, which is the resistance, in this case, of the copper drain tab and the copper clip here. Now, here we've been discussing the ID rating, but the most important thing is, what does continuous current mean? So what we define as continuous current is when a MOSFET reaches thermal stability. And to explain this, we have the graph here, where we do Z theta, which is thermal impedance. And what thermal impedance is that you have a power pulse that you apply to the MOSFET. And as you apply that power pulse, the thermal resistance of the MOSFET can change. And depending on the pulse width, i.e. if you keep the pulse wider, your thermal resistance will go up. However, it only goes up to a certain point. So after 100 milliseconds here, approximately, we can see that the thermal resistance of the MOSFET stays relatively constant or fixed. And this happens after approximately 100 milliseconds. And this is where we say that R theta is constant, and this is a datasheet parameter as well, which we have separately, which is R theta junction to mounting base. And these are two, this is a graph and this is a parameter in the datasheet that we can both see in Xperia datasheets. And you'll see that the max thermal resistance will match up with the graph here as well. Now, we did mention that thermal stability is reached over 100 milliseconds. However, in Xperia, we tested to over 30 seconds in our labs. And this is where the mounting base is kept at 25 degrees. And this is, we have to use a heat sink to keep the temperature under control and at 25 degrees. Now, we just saw what continuous current means. Now, what does this mean as a datasheet parameter? So this is the top one where we have ID, that's the drain current, we have the conditions, and in this case, we're looking at the PSMN R5540 SSH. Now, the very important thing to keep in mind here are the conditions. So we have a VGS of 10 volts, which means that the device is fully on, and we have a mounting base of 25 degrees. If you're in a situation where the VGS is lower, that means that would impact your RDS(on). So if it's, for example, 4.5 volts, that means that the MOSFET isn't as much on as it is at 10 volts, which means that the RDS(on) is higher. And if the RDS(on) is higher, that means that your ID max would be lower. The other condition is the mounting base temperature. Now, if you have an increased mounting base temperature, that means that the power allowance on the MOSFET will start reducing, and that is a linear behavior. So as the mounting base temperature increases, the allowed power dissipation reduces. However, the way this affects the ID rating is actually squared. So because power equals current squared times resistance and power is linear, this then turns into a squared relationship. And the important thing to keep in mind here is that this line here, and this is where we state that 500 amps continuous current has been successfully demonstrated during application tests. This means that unlike many other competitors and most of the manufacturers, we actually test our devices in the lab. And practically the current will be limited by PCB thermal design and operating temperature. Now, the device technologies and the impact. So we just saw what this looks like in a datasheet. How do device technologies impact the datasheet parameter? So the ID max involves MOSFET parameters such as low RDS(on). So this is the resistance of the entire MOSFET, and the R theta, where you have the thermal resistance between the silicon die and out to the surrounding environment. There's also the TJ max, as we mentioned. So you want that to be as high as possible so you can have a good amount of space to work in terms of temperature increase. And then you have bond wires versus copper clip. So copper clip allows for even current spreading. So current can flow easily anywhere within the copper, unlike a wire bond solution. And you also have package thermals. So you want the package to be able to dissipate temperature effectively. And there's also reduced manufacturing steps. So if you have fewer manufacturing steps, that means that you most likely have fewer links or layers against layers of material, which means that you have better thermal performance again. And this also improves reliability. And reliability becomes very important. So in case you have solder voids, you want good reliability and low amount of solder voids so that doesn't impact your MOSFET. And an ID parameter is a parameter which can actually highlight many of these different things. And it's usually the weakest parameter which will limit the ID max rating. Now, it's important to keep in mind that for LFPAC, it's still important to have a good amount of copper both on the drain and on the source to help the device wick away heat. So we discussed the datasheet side of things and the lab side of things, but how does this apply to the application? Lab measurements, they are done in conditions where we have consistency, which means that the results are repeatable and reliable. However, in an application, the conditions may vary. For example, the ideal heatsink, which we have which in our labs, that's kept at 25 degrees. However, in a real application, the mounting base might be different, which would affect the ID capability. And the application max current can therefore be calculated from the ID max rating. So that's why this ID max rating is helpful. You can then still calculate it to your application. And in a lab's TJ max, it can be reached. However, in an application, exceeding TJ max, which is the maximum temperature of the silicon, that is not recommended. And in the lab, we test over 30 seconds. However, in systems or applications, large surge currents, that can be usually under 1 second. And as we saw earlier, between 0.1 and 1 second, that's considered DC for a MOSFET. However, for an entire system and application, that might not be considered thermally DC. And these measurements, they're verified in the lab, where ID max rating is determined when junction temperature reaches the 175 degree maximum temperature, which is usually what our next-period MOSFETs have. And an application, on the other hand, will have safety margins and derating as well. Now, the ID application benefit, as we just mentioned, is that it's a fully tested ID rating on the datasheet. And the ID max rating is underpinned by package technology, silicon technology, thermal performance, as we just showed, and manufacturing quality. And this gives a direct way of understanding complex MOSFET performance in an application when it matters the most. So if we go back to the graph, to the picture Stephen showed earlier with the battery isolation, we have here, where if we short together P plus and P minus, which is where failure could occur, we have these MOSFETs here, which then have to protect the system, which means that they have to turn off. And the time between overcurrent situation happening, so these two shorting together, the circuit detecting the overcurrent situation, and the circuit reacting and attempting to turn off the MOSFET, that period of time is absolutely critical for the MOSFET to be able to survive. And that's where the ID max rating becomes important. Now, we have a similar thing with motor drive applications. The time between the motor, the rotor of the motor locking and the control system reacting becomes critical. So if you have a motor spinning and it locks, that means all of a sudden the back EMF collapses and you have a large amount of current flowing through these MOSFETs here, as the arrows show. And that means that between that time and the control system reacting, the MOSFETs would need to turn off reliably, and they would need to conduct that large current first. So the general rule here that you can set up if you want to make rules is that the ID max capability becomes critical in the time between high system current occurring and the system reacting. So if you have an application and you believe that there might be a time when there is a large system current that could happen, then ID max rating becomes very relevant. And you want that to be handled by the MOSFET, both through conducting and switching off reliably. Now, another thing to keep in mind here is that we can have cable inductances, and that means the second the MOSFET starts switching off, then you need, for example, strong ruggedness or avalanche due to the cable inductances that might exist. Or also you might need safe operating areas. So as the device is turning off, you have to go through linear mode. And when you go through linear mode, safe operating area becomes very important for the MOSFET. With that in mind, back to you, Stephen.
Okay, so yes, we have some products which exhibit this very high current capability. The one at the top you can see is it's in our LFPAC 88. It's a PSMR 55-40 SSH. This has got a DC current rating of 500 amps and a pulse current rating of over 2,000 amps. And also in LFPAC 56, we have PSMR 5125 YLH. So these are very popular in power ordering type applications, or where you'd have lots of MOSFETs in parallel in high current applications, and that's got a DC current rating of 380 amps and a pulse current rating of over 2000 amps. And we have other high current capable parts at 100 volts and, for example, 50 volts. Next slide, please. Okay, so for more information and more resources, please visit our website, nexperia.com/MOSFETs. And from there, you're able to look at any of the videos, some from today, but also previous videos we've recorded on some of these applications. If you need to request samples, please contact your local sales rep or distributor, and you can also buy online at nexperia.com/shop. And we also have a wealth of application notes and some which talk about maximum continuous current in Nexperia LF pack MOSFETs. So with that, I would like to hand over to any questions or comments from those watching.
All right. Thank you very much, gentlemen. Great session. We actually do have a couple of questions coming in for you. Let me start with the first one coming from the audience here. How are measurements in the lab different from theoretical limits?
Steven, should I take that one?
Yes, please.
Yeah, so theoretical limits. So usually the way that is done is that you have RDSON, which is a measured parameter, and you have R theta, which is a measured parameter. And using those two parameters, you then can calculate the maximum allowed current that you can have through your MOSFET. Now, this might not be representative of a real device, because if you actually put a device under measurement, it's usually the weakest link which fails first, which means that if you have a wire bonding, it could be the wire bond structure which is failing, or in the modern devices, you have various different layers which can fail before the actual theoretical limit is reached. So that is the main difference. Our theoretical limit, it does use measured parameters, but it doesn't necessarily capture all the realistic behavior of a MOSFET compared to a real measured result from the lab. Thank you.
Okay. Thank you very much for clarifying that. Bless you, Steven. Second question here, interesting one here as well. What happens if I exceed the ID max rating?
So exceeding the ID max rating in itself is not recommended. So we have that as a datasheet parameter, and we strongly recommend to stay under that max rating. However, if you have an application which all of a sudden crosses that threshold, it doesn't necessarily mean that your MOSFET will break at 501 amps if your MOSFET is rated to 500 amps. And that's not necessarily what will happen. But what we put in the datasheet is the maximum limit that we are confident that the MOSFET will be able to work. And that's where we recommend operating under.
Okay. Thanks for clarifying. Then the third question here. How does avalanching and SOA apply to the ID max parameter?
So, you want me to take that, Stein? Or?
Yeah, you can take that if you want to. Yeah.
Okay, so yeah, if on the SOA plot, there's normally a DC line on the SOA plot, which would be your IDM rating. And that IDM rating is typically about 4 times the ID max. Which is a theoretical max. So this is where we see the 2000 amps. For the avalanche rating, this is an off-state condition. So when you turn the MOSFET off, there's usually inductance within the system. And we would test with an IAS. So most of our high current parts will have an IAS rating on the datasheet. This is something that we do 100% testing. We do for all of these parts, and in many cases it's up to 200 amps that we'll test each product. And this is to take into account any of this high current turn off where avalanche might occur.
Yeah. Can I chime in as well here?
Yes.
Yeah. So it doesn't strictly apply to the ID parameter in itself. However, when you have a large current flowing through your system and through your MOSFETs, you want your MOSFET to be able to most likely turn off that current reliably. And the second, we're talking about turning off a MOSFET reliably, and that's where you would want strong SON and strong avalanching, which is what Stephen was talking about as well. So ID is relevant the moments before you start turning off, but usually you don't want the MOSFET just to sit there and conduct 500 amps. You want it to protect the rest of the circuit. So, yeah.
Okay, thank you for clarifying that. We have another very specific question coming in here related to slide 7, where the question is to please clarify your mention of mounting base temperature versus the junction temperature.
Yeah, so mounting base temperature, actually, you mentioned slide 7, but I'll go back a bit earlier. So we have the LFPAK in profile, and mounting base is this bottom plate here, which is the drain tab. This is where the mounting base temperature is. And the junction temperature is actually on the silicon itself. So it's the difference between what's happening on the edge of the package between the PCB and the LFPAK. That's the mounting base. And the junction is the silicon itself. Yeah, I hope that answered the question.
I hope so too. Then another question here. Does the switching performance, meaning losses and transition time, of a MOSFET worsen as it is designed to handle a higher ID rating?
Stephen, would you like to go that first, Alan? Or?
Yes, we don't. When we optimize our products for the high current rating, the switching performance is not something we would look to sacrifice in those optimizations. So the area where we rely on most for this high current capability is the packaging, the silicon trench technology, and also the quality and reliability. And this is what gives us this high current rating. We don't specifically change our silicon in a way that would impact the switching performance.
Yeah, so I can add a bit to that. So it's this slide here. So it's, as we mentioned to the previous question, actually, which is that if you have a large amount of current, you will most likely want to switch it off. And so from our perspective, we wouldn't want to trade away switching performance to high current rating. And high current rating does depend on quite a few parameters, which also does include RDSON. It does include a lot more parameters as well to it, which we never want to sacrifice for just to achieve a high ID rating. Thank you.
All right. Next question here. With higher currents, does the RDSON decrease? Generally, at how much of ID max do we achieve the highest efficiency?
So the first question is, does RDSON decrease with higher currents? And it's the opposite. So when you have more current flowing through your device, that means your device is heating up. And as your device is heating up, your RDSON heats up. And that's sort of it's an effect that goes against each other. And the more current you have, the more resistance you have. Could you please remind me, what was the second question?
At how much of ID max do we achieve the highest efficiency?
So that is, I'm not entirely sure how to answer that because that is incredibly application specific. Maybe Stephen might have a way to explain this better than I do, but this, because you have efficiencies, for example, in DC-DC converters which would have slightly different, which would look differently in terms of how you measure that efficiency compared to, for example, if you just have a device in an eFuse, where those two would measure their efficiencies in different ways, or different parameters would be important in different ways.
Yeah, I'll add to that, Stein. Normally, the efficiency of an application of a system means that we're trying to reduce losses, and those losses would manifest in heat in the MOSFET. So by putting very high currents through the MOSFET, even though we try to keep the mounting base at 25 degrees C, the silicon's going to get hotter, the system's going to get hotter, and that means that we've now got power losses, and any power losses would affect the efficiency. So in order to get the best efficiency, we want the MOSFET to stay as cool as possible. So they are sort of counterintuitive. One goes against the other, as Stein first said.
Great. So some great questions coming in, and I'm afraid we need to round off here. So again, if you have questions, please do not hesitate to also use the chat function. We have our power experts sitting there also to answer them. But actually, this brings us to the end of this live session. So thank you, Steven and Stein, for this very insightful presentation. And if you want to know more about MOSFETs, please use the resource links underneath the screen. Or as I mentioned, use the chat, and also this presentation is recorded, and also the slides will be available as a download from the website.